So first I want to make sure, can you hear me? Is the microphone working? Okay, very good. So I also would like to thank the organizers for putting together this school and inviting me to take part, and in particular to talk about this subject of topological quantum computing, which is, I think, a particularly fascinating subject for lots of reasons, but I think the main reason is because it's connected to at least two, I think, really deep and fundamental questions about nature. So let me start with just two big questions. So one is a familiar question to anyone who does condensed matter physics. It's one of the central questions in that field, and that is, what are the different ways matter can become ordered? And if you pick up any sort of standard condensed matter physics textbook, you'll find it's filled with lots of examples of sort of the classics, the ways in which matter can order. So for example, crystalline order, magnetic order, superconductivity. And there is, of course, a well-developed set of theoretical tools for characterizing these states in terms of things like broken symmetry and order parameters, and we can study phase transitions between these states using these tools. So this is sort of part of the standard, well, one of the great triumphs of 20th century physics has been the understanding of these sort of standard classic states of matter. But as I imagine everyone here knows, roughly 30 years ago, a new kind of order was discovered. And really, it was in the quantum Hall effect, which is still, I think, today the clearest and best example of this kind of order. A kind of order for which the tools used to describe these states of matter couldn't be applied. There's no broken symmetry in general. There's no locally observable order parameter. And these states, in fact, are what are known as topologically ordered states. So, as I mentioned, quantum Hall states, we can add to that list now spin liquids and topological insulators and related states, topological superconductors, things that I imagine you'll be hearing a lot about throughout this school. One thing I want to point out here is I don't think it's an accident that for the classics, I'm able to show you pictures where these are pictures where with your actual macroscopic eye, you can see manifestations of the order. You can see the crystal facets associated with crystalline order. You can see the lines of force of the magnetic field associated with magnetic order. You can see the Meissner effect. But for these topologically ordered states, all I have is cartoons. And I think that reflects the fact that this kind of ordering is much subtler than and harder to see than the sort of standard kind of ordering we study in condensed matter physics. So that's one big question. And certainly a lot of today's condensed matter physics is focused on better understanding these states, developing the tools needed to characterize them, study transitions between them, and so on. So another big question is, what are the fundamental limits on the kinds of machines we can build? So that may not sound like a physics question, more of an engineering question, but I think it's a question about the universe. Certainly if I were to ask what is the state of the art today in machines that have been built by man, probably something like the laptop I'm using to present this, or the cell phone that everyone has. Everyone has one of these in their pocket right now. A digital computer where the fundamental building block is the ordinary bit. So any sort of switching device, which can be either 0 or 1, and in a digital computer, you might have 100 billion of these things switching on and off, performing some kind of computation. So obviously, that's a very sophisticated machine. But as again, I imagine people here know, roughly 20 years ago, people realized that there was a qualitatively new kind of machine possible, a so-called quantum computer. And in a quantum computer, the fundamental building block isn't the bit, but it's the qubit. So any two-level quantum system, say an electron spin, or quantized levels in a superconducting circuit for a superconducting qubit, and so on, any two-level system will do. And I say a qualitatively new kind of machine because what sparked the revolution here was the realization that if you could build a quantum computer, which was built out of these qubits, and you could manipulate them with sufficient accuracy, that computer could do things no classical computer could ever do. The most famous example being Shor's factoring algorithm, factor an integer into its prime components in polynomial time, rather than exponential, which is the best known algorithm for a classical computer. And here's a picture of maybe of something close to the state of the art here, a 5-qubit quantum computer with 5 superconducting qubits. So here, this is really still a theoretical idea that obviously a lot of today's research is focused on trying to figure out how we can actually do this and if we can do it. And to me, it's really a remarkable fact that these two big questions are really very, very intimately connected. I think something that was, many people have pointed it out, probably the most famously Alexei Kitaev, that somehow this new kind of order, topological order, is really very closely related to the questions that arise when you think about quantum computers and whether you can actually build them. Okay. So this is an important enough point. I want to hammer it home. And to do that, I want to go back in time to prehistory and show you what might have been the first digital device. So this is imagine some piece of slate here, and you have a stone. And the stone can sit on either one side of the slate, and say, on that side of the slate, we'll say that's a 0, or you can put it on the other side of the slate, and that's a 1. So you can store 1 bit of information in this device. Maybe you have to remember, did I hunt today? Do I hunt today or gather today? You switch it back and forth. It reminds you of what you have to do. And it's even possible some enterprising caveman figured out how to market this thing as the iStone and sell it to all of the other cave people. Everyone had to have the latest iStone. And but at this point, I want to point out that even at this level, we can see physics is playing an important role in the robustness of the iStone. And to see that, we can zoom into the stone. And if we do that, if we zoom in sufficiently, we will eventually see the atomic structure. And if we look at it, one sees order. The atoms are arranged in some crystalline array. Of course, the stone itself may not be a perfect crystal, but maybe it's made out of crystalline grains. The point is, the atoms are arranged in some rigid structure, which breaks translational symmetry, and is an example of this sort of classic kind of ordering that condensed matter physics studies. And that's important because for the functioning of the iStone, because that's why when you push the stone from one side of the slate to the other, you don't have to push all of the atoms individually. You only have to push it on one side, and all the other ones go with it. And it may seem trivial, but that's a consequence of long-range order and the rigidity associated with it. So for example, if you imagine you built an iStone, but instead of a stone, you had some droplet of oil. Maybe it's sufficiently viscous that droplet of oil, when you push it from one side to the other, the droplet would move, and for a while you'd be able to tell which side it was on, but it would smudge, and eventually you just have this smear on your slate. And so it's the crystalline order of the stone that makes this classical memory robust. Okay, so that's the iStone. You can store 1 bit. Let's flash forward a bit in history to the iStone 5. This is a Roman abacus. It can store about 20 bits. And let's go another couple of millennia to the iPhone 5. And so there's a jump to 5 times 10 to the 11 bits. This is the discontinued iPod Classic with 10 to the 12 bits. But I want to focus on this because this device uses a magnetic hard drive. And here again, I want to make the point that there really isn't that much difference, aside from scale, between the functioning of the iPod and the iStone. And so I don't know that much about the details of how magnetic hard drives work, but there is a Wikipedia page, and so this is from the Wikipedia page for showing a hard drive, and essentially of course. From my point of view, the essential idea is you store the zeros and ones in magnetically ordered states, where if the magnetic moments are pointing one way, it's a 1. If it's pointing the other way, it's a 0. I think in reality, it's associated with domain walls, so there are cleverer ways to store the information. But for our purposes, let's just imagine you store the 1s and 0s in magnetic domains with the spins pointing one way or the other. So here's just a cartoon of such magnetic order. We have some spin 1/2 particle, an electron, say, a square lattice array. And let's imagine there's some Hamiltonian with an Ising-like Hamiltonian with a doubly degenerate ground state. where the spins are either pointing up, that could be the 0, or pointing down, that could be the 1. And again, the idea here, the idea I want to emphasize, it may seem maybe a fairly basic idea, but that is that again, it's the long-range magnetic order here that makes this a robust memory. If one of these spins flips, let's say, an error occurs, eventually, due to the interaction that spin has with the other spins, it will eventually realign itself. And so again, it's the long-range magnetic order that makes this a robust memory. So that's great for a classical bit. And in fact, essentially, what's happening here is the physics of magnetic order is providing a kind of error correction for your classical memory. But it would be terrible for a quantum bit. Even if I could somehow put some magnetic domain in a quantum superposition of these two states, 0 and 1, on some unimaginably short time scale, that state would lose its quantum coherence due to its coupling to the environment. And the reason is simply the environment, just as we would have no trouble telling the difference between these two magnetic domains, they're macroscopically distinct. The environment also has no trouble. And so very quickly, the environment becomes entangled with your superposition, and you lose the quantum coherence. So this is a terrible place to put a bit. Sorry, a qubit. But there's another kind of order. And even at this cartoon level, I can give what I would argue is one of the simplest examples of this kind of order. And to see that, let me remind you that spins, one of the things spins can do, they don't all have to point up or point down. They can also form singlets. With pairs of them can form singlets. And we can represent that singlet with this valence bond, this sort of notation which you probably first saw in high school. Yes?
What is meant by decoherence?
Sorry?
What is meant by decoherence?
I'm sorry.
What's decoherence?
Decoherence is, but what's the question?
What's the meaning of decoherence?
What's the meaning of decoherence? So, so let's say I somehow put so let's call it a 0 and a 1. So the 0 is the state where all the spins are pointing up, and the 1 is the state where all the spins are pointing down. So that's my qubit, and I put it into some particular quantum superposition, some pure quantum state. But then it's coupled with the rest of the universe. And for a state like this, with long-range magnetic order, it's very easy for the environment to detect which of these states we're in, whether we're in the 0 state or the 1 state. So over time, the coupling of these two states to the universe will lead to some, say, call this 1, some state like this. So I use the word entangled. This is a state where the states of the qubit have become entangled with the universe. And this is no longer this. If I trace out the universe now, the description of this state would be a density matrix describing a totally mixed state. So there's no distinction between a state like this and just having an ordinary bit where I don't know. There's some probability it's 0, some probability it's 1. And from the point of view of quantum computing, this is death to your quantum algorithm. It's crucial as you carry out your computation to maintain your qubits have to maintain their coherence. So does that answer the question? Okay. So that's the problem with this kind of order. So, but as I say, spins can also form singlets, and so let's imagine the spins on this lattice form some particular singlet pattern. Here I'm using periodic boundary conditions, mainly because I don't want the bonds to get too long, the valence bonds to get too long. So rather than taking this bond and trying to connect it all the way across here, I imagine it goes around here. So this is sort of a theoretical thought experiment I'm doing here. I wouldn't know how to actually do this in reality. Okay, so if you look at this pattern, there doesn't appear to be any order. I can throw down these bonds any way I like. But if you look at it carefully enough, one eventually sees there is some sort of hidden order. And to see that, what we can do is slice through these columns and count the number of bonds that we cut. So here you can see we cut 1, 2, 3 bonds, 3. Here we cut 1. Here we cut 1. Here we cut 1. If I slice through here, you'd see it's also 1. And the pattern here is that all of these numbers are odd. And this is something you can check for yourself in the privacy of your own home. If you draw a square lattice with an even width, any valence bond configuration you draw like this, you slice through, you'll find either all odd or all even numbers of bonds sliced. So just as in a benzene, which is probably the context where you first saw valence bonds in high school, these bond configurations can resonate. And here the crucial point is if there's a local change in the bonds, the number of bonds we slice changes, in this case here from 1 to 3, but the parity doesn't change. So local rearrangements of these bonds don't change the fact that all of these numbers are odd. So again, just as in benzene, the true ground state is a state where you have resonance between the two possible valence bond configurations. Here you can imagine constructing a state where you superimpose lots and lots of these valence bond configurations, but let's make sure we only superimpose those states where we slice an odd number of bonds. And so just superimpose a bunch of these states, and we get and form some quantum superposition. And this is, of course, an example of a spin liquid or an RBB, resonating valence bond state. And if I form the superposition, it's no longer meaningful for me to ask how many bonds I slice when I cut through. But what does remain is the oddness or the evenness. Because the state, you have to imagine, is a quantum superposition of lots and lots of states, all of which have an odd number of bonds sliced by these lines. Okay. As I mentioned, there's also the possibility that the number of bonds you slice is even. For example, here, 2, 2, 0, 2. Again, local changes don't change the evenness. So you can form a superposition over lots and lots of these valence bond states, all of which have this even feature, and form a spin liquid there. And the point is, these are distinct states. We have two states here, two of these spin liquid states. One is the odd state, and that's a place where we could imagine putting our 0. Again, I don't know how to do this in practice. This is just a simple example to start with. And we could put our 1 in the even state. And the point is, in that case, the 0 and 1 states are no longer these macroscopically distinct states where you have long-range magnetic order pointing one way or the other. It's this much subtler order, which you can't measure locally. To measure this order, you somehow have to imagine slicing through the entire lattice, performing some global measurement. And just as that's hard to do in practice, if you're observing these states, it's hard for the universe to detect. And so one would expect that states like this, if I formed a superposition, would last much longer. They would maintain their quantum coherence much longer than the superposition of the two ordinary magnetically ordered states. Yes?
Can you do a state that cuts odd number of bonds in one region and cuts even number of bonds in another?
You mean, do you mean when you say one region, or you mean, let's see.
Like for some of the bonds.
Yes.
In some region, like he built some states that
yes.
connect the dots in some regions.
Yes, yes.
So
I think you'd.
Yeah,
I'm not sure what you're asking, but one thing that might happen is let's say maybe I'll say something about this later, but if you create an excitation, so-called spin-on excitation here, you'd have to break one of these bonds and move the other spin away. And for such an excitation, you'd have a domain wall between even and odd.
Yeah.
But if I insist that, this is really a statement about lattices and drawing lines between points. I mean, if I insist on that every site is paired with another site, then you always get this even odd pattern.
With periodic boundary?
With periodic boundary conditions, yeah.
If you cut horizontally
yes.
between the second and third row, it looks like you cut 4.
Between the second and third row. So here it's 1, here it's 4. 1, 2, 3, 4. So I've been lying. That's odd, even.
Yeah.
Okay, but I claim I haven't been lying. So can anyone guess why? Why is it? So you're absolutely right. Odd, I hadn't noticed that, but odd, even, odd. Now it's 3. Well, but even if I didn't have, even without periodic boundary conditions, I'll just tell you because there's, I mean.
You have 5 dots on the row.
That's right. I mean, so I think I mentioned in passing, this is my legal defense, that the width had to be even. So for an even width strip like this, you'll always get either even or odd. For an odd width strip, you'll always get alternating even, odd, even, odd, even, odd. I could play the same game there where one state would be the even, odd, even, odd, even, odd, even, odd sector, and the other would be the odd, even, odd, even, odd, even. But you're absolutely right. So the statement that it's always the same parity requires this to be an even width strip. Yeah.
I didn't quite catch why this decouples from the environment.
Well, I think, well, again, I think it's because it's hard to see. It's hard to tell. In fact, well, let me try to answer that question with a demonstration. Let's see, I think that's what's coming next. Yeah, okay, so what I'm claiming is exactly what you asked. I'm claiming that we could, if we formed a superposition of this 0 and 1, it would be protected from decoherence. And so to make that point, what I'd like to do is an experiment. So in this experiment, I'd like you to be the environment. And I'm going to show you, first I'm going to show you an ordinary magnetically ordered state. And it's either in the 0 state. Remember, the 0 state, I defined it to be when the spins are all pointing up. And it's a 1 state when the spins are all pointing down. So you're the environment, and I want, now, this is hard, you know, if you can bring yourself to do this, it would be great. I know if you could just shout out either 0 or 1 the moment you know whether it's a 0 or 1. At least that will get, wake everyone up. So I'm going to show you an ordinary, again, it's an ordinary magnetic state. Spins are pointing up, 0. Spins are pointing down, 1. You're the environment. Ready? Go.
1, 0.
Okay, that was actually the best. I've done this a couple of times. That's the best. But it's still kind of sad. But that's the best. So as long as you remember, and I mean, of course, it depends on. But the point is, I think, if you remember, up is 0 and down is 1. As soon as you look at this, you can immediately see, because you don't have to look at the whole. You don't have to somehow take the whole thing in. If you just look locally, you can tell. Oh, these spins are pointing up. I know it's magnetically ordered. These are pointing up here. They're going to be pointing up there. So it's just immediately obvious. You look at it and you can immediately see it's 0 or 1, and that's the origin of this this rapid decoherence. You just played the role of the universe there. Okay, now let's try the same thing with the qubit in the spin liquid. So now I'm going to show you a valence bond configuration. Remember, the rule is if we slice down, if it's even, if it's odd, it's a 0. If it's even, it's a 1. So if you slice down the columns, if it's odd, it's a 0. Even, it's a 1. Again, you're the environment. Shout out either 0 or 1 when you know what it is. Ready? Go. I don't have a watch. But 1. Right. So unless I screw this up, which is possible, but if you slice, so it does have an even width. If you slice through, you'll see. Well, the easiest to do is on the side here. So there's 1, 2, 3, 4. So it's even. And I think if you slice down any column, you'll find it's even. Of course, I could have made it harder for you. Oh, I missed it. I have a slide missing here. I could have tried. I could have, instead of showing you this picture here, I could have shown you the sort of abstract gray spin liquid. But of course, there I'm playing games because it's very hard to write down quantum superpositions with classical power point. Whereas I have no trouble writing drawing pictures of the classically ordered magnetic state.
So why do we believe the coupling to the universe is local?
Well, I mean, it's if you imagine writing down some Hamiltonian that describes the coupling of the universe to some real physical system, say. So let's say it's you have electrons in quantum dots coupled through to say the nuclear spins. The Hamiltonian you write down in that case would be the contact interaction. Some local, I mean, the underlying interactions you have to assume are local interactions.
Right, but there are long-range interactions.
There are long-range interactions. In the big picture, I mean, this is I would say still almost it's an experimental question because people have not. I mean, this idea of storing the information globally isn't just relevant for topological order. It's also relevant for all of the so-called field of quantum error correction. And there again, the underlying assumption when people prove things like you can build a quantum computer, there's a finite threshold, error threshold. They make assumptions about the nature of the decoherence, and the state of that field now is you have theory, and the experiment is beginning to catch up. I think there is a chance, while I think I have my doubts I'll be around for the first quantum computer, I think we are going to see, in fact, we're beginning to see the first experiments on quantum error correction where people with ordinary quantum computers create states like this and start measuring their decoherence properties. But I think to answer your question, the underlying assumption is that I think if you have long-range interactions, but again, if they're power law, there's still some hope that, in some ways, of course, the question you're asking is similar. You can prove theorems about the robustness of classical machines, classical computers, but that doesn't mean they're robust against an error if a meteor flies and crashes into your computer and destroys it. That's a long-range error that destroys all of the bits. I guess I think this is a good question, and the best answer I have is the simplest models. The models people have considered are short range, and then including with exponential fall-offs, and I would say that's a subject of current research. And the good news is I'm hopeful that it will soon become a field of experimental research. People will start being able to study these coherence times and what the effect of creating these states is. Yes.
Is long-range entanglement a very key thing here?
So this is a cartoon of a spin liquid. And actually, I probably would have to say more to say specifically what kind of spin liquid. But let's say it's a Z2 spin liquid. It would, if you were to calculate its topological entanglement entropy, it would have one. There would be a subleading correction to the area law, which is.
So is there a key thing in encoding information? Like if you have short-range entanglement?
Yes. I think so. I mean, I think if you want to, I mean, in order to, I mean, so this is, I mean, of course, these are what I've shown you is sort of the simplest cartoon examples of conventional order and topological order. And again, conventionally ordered states are states characterized by broken symmetry with multiple ground states and distinguished by locally observable order parameters. And topologically ordered states, of course, the notion of topological order is not so well defined. And so for my purposes, for most of this talk, I mean topological order in the sense of, at least one of the senses of when, that you have a ground state degeneracy on topologically non-trivial surfaces. So these are, in general, I'm going to be talking about two-dimensional states. And with an energy gap. And the point I'm making here is it's a fact, and it's been true since the days of the eye stone, that conventionally ordered states are provide nature's classical error correction. And one of the insights into that's come from topological quantum computing is the idea that these topologically ordered states are indeed, they play the analogous role for quantum information that conventionally ordered states play for classical information. Okay, so still at this cartoon level, let me just make a few more points about the distinction between topological order and conventional order. And I guess by way of motivation, I can say, in this toy example, I haven't talked about how you could actually form a particular superposition or how you could manipulate the state to carry out a computation. And to do that, we need to say something about the excitations. So in conventional order, for conventional magnetic order, if I create an excitation, I do it by just going in and locally flipping a spin. So, and in doing that, I create a magnon. And the net result is a total, the SZ here changes by +1 because spin down is flipped up, spin down 1/2 is flipped to spin up 1/2. So that's a conventional, ordinary quasi-particle excitation in a magnet. For the case of topological order, if I do create an analogous local excitation, I would do it by finding some bond and breaking it, going from a singlet to a triplet. In this case, having the two spins pointing up, let's say. So again, any local change I make changes the SZ by 1 here. But the new feature, which is, again, a very common or fundamental feature of topologically ordered states, is this excitation fractionalizes. We can pull these spin 1/2 excitations apart. These are so-called spin-ons. And so the excitation I create with some local operator fractionalizes into excitations which I can't create with a local operator. Okay. Now, of course, the gold standard of topological order, and arguably probably still the only absolutely certain case of at least the kind of topological order I'm talking about here, is the fractional quantum Hall effect, where I'll just remind you, you have a gas of electrons in 2 dimensions in a magnetic field, and those electrons can, the filling fraction is, the Landau level filling fraction is a rational fraction. They can condense into some incompressible quantum Hall fluid, and this fluid can have many similar features as the spin liquid. For example, fractionalization. If you add an electron, the electron fractionalizes into fractionally charged excitation. So for example, for the nu equals 1/3 state, it breaks apart into 3 charged E/3 excitations. Also there's a topological degeneracy for the nu equals 1/3 state. If you put the state on a sphere, there's a unique ground state. If you put it on a torus, there's a 3-fold degeneracy for nu equals 1/3. And in general, for genus n, it's 3 to the n-fold degeneracy. And just like for the spin liquid, these states, these distinct states, cannot be distinguished by local measurements. You have to perform some global measurement. You have to measure somehow all the way around a cycle of the torus here to determine which of these states you're in. So again, you could imagine if you could somehow engineer a 2-dimensional electron gas on a torus, you could somehow create a kind of qubit. But again, it's very hard to imagine how you would actually do that and how you would manipulate that qubit. Yes?
So in the previous spin liquid example, where does the topological non-trivial surface come into play?
Well, yeah, maybe so here, so you remember what so one of the reasons I chose periodic boundary conditions is because I wanted to have both odd and even. So I think, if I didn't choose periodic boundary conditions, I would still get this pattern, but I would only get either all odd or all even. So what I should, for the example, I was actually on a cylinder. Though, as someone pointed out, when they sliced it this way, they found the odd, even pattern. But let's say it's an even by even lattice for simplicity. That means, and with periodic boundary conditions both in the x and y directions. then if I slice, I'm always going to get either even, or odd, 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 and I'll get even, or odd, odd, odd. So there are then for this case, there are 4 possibilities. And in fact, you can show if you have a higher genus surface, the degeneracy goes as 4 to the power of the genus. So this is, again, a simple, yeah.
So for the quantum spin liquid example, how can I imagine constructing a 2-genus surface, and how can I see that it has a higher degeneracy?
So the first, how can you imagine constructing mean in the real world?
Yeah, like periodic boundary conditions, like easy to imagine. But how can I imagine making one with more holes?
Well, I can certainly draw the picture of the donut. I mean, yeah, that's a good question. I mean, I don't know if I had to actually.
Why does it have more degeneracy? Can you see by drawing rings?
Yeah, I think so. Yes, yeah. So, yeah, that's. Let me go here just because I have higher genus. So yeah, I could, associated with each cycle, there's this odd or even quantum number. So here I have more cycles, and from those there will be a higher degeneracy. I suppose you're asking me to actually prove it's 4 to the G. I'm not sure. I mean, I probably could do that, but
4 to the G. So there we should get 16.
That's for the spin liquid.
Yeah,
for the Z2 spin liquid example.
Right,
yeah.
the spin liquid should be 16. So on that donut with 2 holes, it should be 16.
Let me just pause and make sure I agree with that, and I believe the answer is yes.
Okay.
I do.
Yeah.
So let me do what I usually do in a real class: is say, "Good question. Let me assign it as homework."
Any quantum numbers to define fractionalization?
You mean there has to be some quantum number to begin with that's fractionalized?
Right.
I guess I think yes, but I don't.
There are no known examples
Without, well, let's see. Now, this is a good question. It seems to me there's got to be some. I mean, when you perform some local operation, let's see. I at least don't at the moment. I can't think of any examples of fractionalization where I don't have some good quantum number that is then fractionalized. So, but I actually don't. I don't know if it's absolutely necessary. But it's a good question. Let's see. Okay, so this is all to set things up for the following statement, which is, fortunately, from the point of view of trying to actually use this degeneracy to build a quantum computer, there exists a kind of topological order which is particularly exotic, or at least it exists in theory, and there are at least some experimental systems where it seems almost certain to be relevant. And this is so-called non-Abelian states. And let me start with the non-Abelian fractional quantum Hall states, which is these are the original. This is the origin of this notion, which goes back to this paper by Moore and Reed. And let me just tell you the properties of these non-Abelian states. Again, we have fractionalized quasi-particles. But the new feature here is if you have a collection of these quasi-particles and they're well separated and localized, held in place somehow, there is not just a unique state, but there is a degeneracy. There's a degenerate Hilbert space. And furthermore, that Hilbert space is exponentially large in the number of these quasi-particles. So there's some big Hilbert space associated with some topological quantum numbers like the odd evenness, but it's sort of harder to draw pictures of. And just like the spin liquid example, these states can only be distinguished by global measurements. In fact, one has to somehow measure a region that encloses 2 or more particles. So if the particles are well separated, if I perform some local measurement here, I can't tell what state I'm in this big Hilbert space. We have these topologically degenerate states. Again, one can expect that it should be protected from decoherence, at least more than conventionally ordered states. So this is a perfect place to hide quantum information. And in this case, we can actually think about how to manipulate it. And to show you how we can do that, let me just tell you or remind you about some interesting, unique features of exchanging particles in two space dimensions. So again, these are two-dimensional states of matter. So imagine I have, say, 3 quasi-particles here. And if I exchange the bottom two, I can exchange them, so let's say, in a clockwise sense. And if I do that, and I include the time dimension, you can see their world lines sweep out what are known as braids. Sweep out a braid in 2 + 1 dimensions. And what does that mean? Well, it means that if we imagine we took the same 3 particles and I exchanged the same 2 particles, but instead of in a clockwise sense, I did it in a counterclockwise sense, we get a distinct braid. You can see this braid, if I drew it correctly, is not topologically equivalent to this braid. There's no way I can continuously deform this and turn it into this. And this just reflects the fact that in 2 space dimensions, we can distinguish between clockwise exchange and counterclockwise exchange. To put it another way, exchanging particles in 2 dimensions is not necessarily its own inverse, which is in 3 dimensions it's the case. Exchanging particles is its own inverse, and that's the origin of the usual argument for why identical particles are either bosons or fermions. If exchanging is its own inverse, it squares to 1. And so the effect of exchanging is either going to give a +1 for bosons or -1 for fermions. But in 2 space dimensions, exchange is not equal to its own inverse. It doesn't square to 1. And so there's the possibility for richer kinds of statistics. And so the simplest example is just the ordinary fractional statistics. So again, if we have an ordinary so-called Abelian state, then if I have some quasi-particles present, there's still going to be a unique state. And if I exchange these particles, I have to come back, and I bring them back to the same position, I have to come back to the same state, but we can acquire a phase. Again, the usual argument for the statistics of identical particles is, well, if I exchange particles twice, that's equivalent to the identity, and so this phase has to square to 1, so it has to be either 0 or pi, or plus or minus 1 for bosons or fermions. But in 2 space dimensions, one has the possibility for arbitrary complex phases. It can be complex because it has one, if it's e to the I pi over 3 for a clockwise exchange, it's e to the minus I pi over 3 for a counterclockwise exchange. And so, for example, for the nu equals 1/3 fractional quantum Hall state, this phase is pi over 3. Now, things get really interesting when we have one of these non-Abelian states where when we have our localized quasi-particles, we don't just have a unique ground state, but we have a Hilbert space. And let's say it happens to be 2-dimensional. So then our initial state is going to be in that Hilbert space. It's going to be in some superposition of psi 0 and psi 1, some basis states for this Hilbert space. And if I exchange these particles, I'll have to come back, if they come back to the same position, I have to come back to the same Hilbert space, but it no longer has to be the same state. In general, it will be a different superposition. And we can represent these states with column vectors, and we see here, exchanging particles in these non-Abelian states doesn't just result in a phase factor, but results in a matrix. And furthermore, because we're in 2 space dimensions, and because exchanging is not equal to its own inverse, it doesn't square to 1, these matrices don't have to, in general, won't square to 1. If they squared to 1, they would be trivial, because then it would tell you that the matrix operation would only depend on the permutation of the particles. But in 2 dimensions, the matrix at least can depend not just on the permutation, but the actual braid used to permute the particles. So a mathematician would say these matrices form a non-Abelian representation of the braid group. Okay, so this is of course the essential idea of topological quantum computation. The idea is that you could one way to envision building a quantum computer is to produce one of these states and one of these non-Abelian states, and we have a collection of these non-Abelian anyons fixed in space. We have this big Hilbert space. That's the space we use to put our to store the information in our computer and process it. And the way we process it is by braiding the particles around each other. And from the properties of these non-abelian anyons, we know that braiding them around each other will result, as long as we keep them far enough apart while we do it, will result in some unitary operation acting on this state, the initial state, bringing us to the final state. And again, I'll sort of emphasize this point. This matrix, if these exchanges are squared to 1, this matrix would only depend on the permutation of the particles, which is too trivial. That's a finite group. And so you wouldn't be able to do quantum computation. What's crucial here is it depends on the actual braid. And furthermore, it only depends on, two braids that are topologically equivalent produce the exact same matrix, again, provided the particles are kept far enough apart. So the ingredients here are this Hilbert space, this topological Hilbert space, which, like the spin liquid example, has some built-in protection from decoherence. And a means of manipulating this space by braiding particles that, again, is robust in that if I, as long as I carry out the braid and it has the same, or it's topologically equivalent to the braid I want to carry out, I'm not making any errors. And so, of course, this is the brilliant idea, really, of Alexei Kitaev. And the particular brand of this topological quantum computing I'll be talking about most is also closely related to this paper by Friedman, Larson, and Wang. OK. Yeah?
So here, one basis or commuting basis would be sort of position of the anyons?
Well, no. No. Good question. The anyons are fixed. So I want to imagine the anyons are fixed in space. So the basis now is now I have this funny topological Hilbert space. And actually, I will be talking about how to label those basis states and even count them. But in talking about the space, I'm imagining the particles are fixed. So in fact, if the particles are fixed, then the particle positions don't. You still have this big Hilbert space, and you have to label it with quantum numbers, which we'll talk about.
Well, I'm trying to think how you start with a superposition.
Or how would I initialize the computer?
Yeah, exactly.
OK, so these are things I will get to, but just to mention here, if you want to, if you imagine pulling particles. So again, this is an easy thing to talk about, hard to do experimentally. Pulling say a quasi-particle quasi-hole pair out of the vacuum of a fractional quantum Hall state. Those, if it's a non-abelian state, these excitations have non-abelian statistics, and they come out in a particular state, which has the same quantum numbers as the vacuum. And so using that, that's a way to initialize. You can pull these anyons out, and you've initialized it into a particular state. Then you can compute by braiding them around each other. So one of my goals in these lectures is to sort of give you at least one example where I can tell you about all of these steps. So I'll be coming back to these issues. Yeah?
If it's topological, the pairs they come close together as long as they don't hit each other.
Good question, because it's not that topological. Well, these quasi-particles have a finite size, finite extent. For example, in the fractional quantum Hall context, their size is roughly given by the magnetic length. And so when the particles get close together, so one of the things that can happen is they actually interact with each other, and that can lead to additional phases which are not topological. So I think that maybe that's the best way to let me see if I can come up with a better, because I am going to talk about this also. So if you have two of these particles, these topologically distinct Hilbert space, well, maybe one way to answer that is also this. Remember, I mentioned that in order to distinguish the states, you have to perform a global measurement. And by global, that means enclosing two or more particles. And if you keep them far apart, it's very hard to perform such a measurement. So as you bring them together, you can actually begin to. It actually is possible to distinguish locally. There's a local. I mean, the charge distribution will be slightly different in these different states when you bring the particles together. And if the charge distribution is different, the environment can see. So, it's really crucial to, if you want to, it determines how long range the measurement has to be to determine what state you're in and how far you keep the particles apart. And another way to, I mean, if you bring them together, the states are no longer distinct, and furthermore, they have different energies. So just the ordinary quantum mechanical e to the I et phase will also produce some non-topological contribution. So that's a source of error in this kind of quantum computing. You want to keep your particles far enough apart.
The distinction between non-abelian ground state degeneracy of a non-abelian system versus the abelian system on a higher degenerate surface.
Yes.
Because they also have a degeneracy.
They also have a degeneracy. I mean, maybe this is too technical an answer. One distinction is the degeneracy for an abelian state counts the number of distinct quasi-particle excitations, but in a non-abelian state, well, I guess that's still true. Sorry, in a non-abelian state, but the quantum dimension is different. So I mean, I guess yes. I mean, there is still, you still have a ground state degeneracy. It doesn't have the simple form of say 3 to the g for the abelian U equals 1/3 state.
Excuse me.
Yeah.
Maybe this is a silly question, but I would like to know, why do we identify the exchange phase as grading phase?
When you say exchange phase with grading phase, well, let's see.
By exchange phase, I mean, if we have two quasi-particles, we exchange their position in the phase that we obtain. And by grading phase, I mean, we really do this grading process, the phase that we obtain.
So maybe, I'm not sure, maybe, so one of the things I'm sort of glossing over here is of course there could be, especially for the abelian case, there will be other sources of a phase, contributing to the phase. For example, in a fractional quantum Hall state, there's an enormous magnetic field, so there's always an Aronoff-Bohm phase, which is geometric. It doesn't just depend on the topology. I guess the point is in 2 dimensions, there's at least the possibility to have a contribution to the phase, which does just depend on the topology of the exchange.
I think what he means is just if I just have a wave function and just in the wave function switch the particles, why is that the same as actually time evolving the system and moving it around? I think that's
yes.
So it looks the phase that he just said is a structure of the Hilbert space, but the grading phase is a property of the Hamiltonian. Why are they necessarily related?
Well, it's another good question. If I have a collection, so I guess in some sense I confess I think sort of operationally, if I have a collection of non-abelian anyons, I have a Hilbert space, and if I want to talk about exchanging them, I really do have to, at least I, think about physically exchanging them and what the effect it has on that Hilbert space. And in fact, the Hilbert space of these particles is a strange Hilbert space. We'll see that. And we'll talk about what the effect of exchanging these particles are. And so if we want to write down a wave function for a collection of non-abelian particles, I mean, remember the idea here is the particles are fixed in space. And I can't, if I write down a wave function and I just interchange the position of 2 of the particles, it's not enough to tell me what the final state is. I need to know how they were exchanged. So I think I'm dancing around your question by saying so for my purposes, the easiest answer is I'm always thinking of the thought experiment and hopefully one day real experiment of actually moving these particles adiabatically around each other.
Okay, thank you.
Yes?
Another way to put the question, I don't know, maybe it's related or not related. So is there a relation between the braiding operation and the Hamiltonian? Like commuting or doing something like that?
Well,
braiding operation in the sense, like exchanging particles.
Right, you're exchanging quasi-particles. So, I mean, obviously, if you wanted to do that with a you might have a Hamiltonian describing some fractional quantum Hall state, then you'd add a perturbation describing some potential that locally captures two quasi-particles, and then you'd adiabatically move them around each other. So you certainly can write down such a Hamiltonian. But the Hamiltonian itself, at least the Hamiltonian I would write down, is the one that describes the electrons, and that's just an ordinary, this is some emergent. These quasi-particles are some emergent fractionalized quasi-particles, which are non-local objects. And so, well, again, I think I'm hopeful that some of these questions will be partly answered as the lectures go on, but they're all good. So. Yes.
For a case of very close particles, if you just exchange two of them, you're going to get a phase.
Not necessarily. We'll see that as well. I mean, because I have here, in this case, for this example, I imagine I have a two-dimensional Hilbert space. If I exchange these particles, well, yes, okay, there's going to be some basis in which it's just a phase. But in general, it's not a phase, not just a phase. We'll see, so it has to do with the topological charge of these particles, of the pair of particles. Yeah.
Thinking of real implementations,
Okay.
probably it's related to the questions.
Yes.
How important is this? In the next slide, we have all the particles aligned.
Oh, that's not important at all. That's
Right.
just from the point of view of PowerPoint.
No, I mean, but how important is that the time evolution, that the exchange is?
It's a good question. So another feature of this is they start out at the same point and they end at exactly the same point. But that's in reality what you would do is you pull them out of the vacuum, braid them around each other, and then try to recombine them into the vacuum. So actually, a better diagram here would be I would tie both ends of these, and this braid would become a knot, and then it doesn't matter whatever knot you created, it's topologically equivalent. Will carry out the same computation. So that this is a very artificial picture. Okay. So just to get rooted in at least some reality here, let me talk about at least two possible non-abelian states. You'll be hearing about more examples of possible realizations of non-abelian quasi-particles throughout the course. But sort of, the granddaddy of all of these states is the nu equals 5/2 state. And so this is some fractional quantum Hall data showing a plateau at nu equals 5/2. This state is almost certainly the so-called Moore-Reed-Foppian state, the original state proposed by Moore and Reed when they also introduced this notion of non-abelian statistics. And the fractionalized excitations have charge E/4, and they are, in fact, Ising anyons, which are the type of non-abelian enyon which is associated with Majorana bound states or Majorana zero modes that you'll be hearing a lot about throughout these lectures, and you read a lot about in the pages of Nature and Science these days, because there's a lot of excitement and real experiments and the potential for realizing them. Although, and as I say, I think the theoretical case that the 5/2 state does indeed have these kind of excitations is very strong. The experimental case is still uncertain, but there are good prospects here, as there are in the context of topological superconductivity for other schemes for creating Majorana bound states, that fairly soon there will be clear evidence that these excitations really exist. But one feature of these excitations, or not a feature, bug, I guess, from the point of view of quantum computing, is their particular brand, the braiding properties of Ising anyons are not, how am I doing on time?
Yeah, I guess you are already beyond.
Oh, is that right?
30. Oh, okay. 10:45. Okay.
10:45. I thought, we started at 9:30.
Oh, yeah, sorry.
So I think, yeah. Okay, so, when I say braiding alone is not sufficient for universal quantum computation, that means you can't carry out arbitrary unitary operations by braiding these anyons. And this is something I'll actually come back to and even show you. You may also hear about that in other lectures. So I at least want to start by talking about another, I would say, much more theoretical, currently flavor of non-abelian enneon. But at least there's at least a prospect, although a very, I would say, a much dimmer one. The case is nowhere near as strong. But it's at least possible that this nu equals 12 fifth state is a so-called Reed-Rezai parafermion state. These are fractional quantum Hall states proposed by Reed and Rezai, for which, for this particular state, the fractionalized quasi-particles have charge e over 5, and they're morally equivalent. When I say morally, it means up to irrelevant abelian phase factors, which I'm not going to worry about, what are known as Fibonacci enneons. And you'll see why they're called Fibonacci enneons if you don't already know soon enough. And the nice thing about Fibonacci enneons is that braiding is universal for quantum computation. That's one of the things that was proven by Friedman, Larson, and Wack. So arbitrary, so you can always find some braid to carry out whatever quantum computation you want to carry out. And I'll even say something about how you actually do that. Now, so I want to focus on Fibonacci enneons. And here, the one problem is when talking about the Ising enneons and Majorana fermions, one can use some of the standard toolkit of condensed matter physics. You can write down creation and annihilation operators and solve the Bogoliubov-Duchenne equation and sort of do standard things, and out these particles pop out. For Fibonacci enneons, there's really no such simple language. So the best way I know how to introduce them, and let's see, so I have another 15 minutes or maybe 10 or 15 minutes so I can at least start this process. So the best way I know how to introduce them is to create a universe from nothing. And physicists have big egos. So, and just create these particles out of nothing. And in the process of doing that, we'll sort of see their properties. So if you'll indulge me, let me go to this blank screen, which represents a formless void. And then because my student tells me to do this, so I say, let there be light. And we are. So there's our universe. And it's kind of boring. There's not much going on. So let's create something to put in the universe. Let's create a particle. Now, okay, that's nice. But what does it mean to have a particle? To have some meaning, we have to give it some attribute. So what I'm going to do is assign it a kind of charge, not to be confused with electrical charge, but some property, and which is defined in the following way. If I can always, if I consider some region, some boundary, I can always ask, what is the enclosed charge? You can think of this as sort of a Gaussian surface. And if I look at a boundary over here that doesn't enclose any particles, the enclosed charge is 0. But if I enclose a particle, the enclosed charge is 1. So that gives some meaning to having a particle. There's some measurable observable that tells me I have a particle. Okay, so that's good. But still kind of boring. So the next step in our universe creation is to consider two particles. And for these two particles, again, I can talk about this charge. And so over here, the enclosed charge is 0. Here, the enclosed charge is 1. Here, the enclosed charge is 1. But now, in my role as creator of this new universe, I am faced with a question. What's the total charge of this pair? And so here, I can make, there are several choices. If this was indeed ordinary electrical charge, it would just be 2. I would just add it. That's the rule for combining ordinary charge. But I want to keep my universe simple. I don't want to have charges, any other charges beyond 0 and 1. So I don't want to allow for charge 2. So one thing I could do is I could define the charge mod 2. That's actually a perfectly valid choice. And that leads to an abelian theory, which is not related either to the Kitaev-Torah code or the so-called doubled semyon model. But what I would like to do is I want a non-abelian state. So I can take my inspiration from, say, ordinary spin. If these were ordinary spin 1 particles, if I combine them, the total spin could be 0, 1, or 2 by the usual rule of adding spin. But I don't want to have 2, so I just, the rule is it can be either 0 or 1. And I just enforce that. So this is an example of a fusion rule. And I can write it like this. So this is, for ordinary spin, if I tensored the two spin 1 representations, I would get the direct sum of either 0, 1, or 2. But I'm throwing out the 2. And this is my fundamental fusion rule. And then there are other trivial ones, which is if I fuse charge 1 with 0, I get 1. Or 0 with itself, I get 0. And again, and another distinction between this and ordinary spin is there's no analog of the local SZ quantum number. There are no local degrees of freedom. There are only degrees of freedom, global degrees of freedom associated with pairs with 2 or more particles. So what does this mean? It means that if I have these two particles, they can actually exist in a quantum superposition of a state with total charge 0 and total charge 1. So by making this choice, if I have two particles, I now have a two-dimensional Hilbert space. Again, if you want to think in terms of spin, it's like we have spins with this funny fusion rule, and we only talk about total spin quantum numbers. We never talk about SZ quantum numbers. Okay. And here, of course, we can see, although I've built it in by hand in this universe, but we can see this important feature of non-abelian particles, which is at the heart of why they are potentially useful for quantum computing. And that is that the particles are well separated. In order to tell whether their total charge is 0 or 1, I have to perform a measurement. I have to determine the charge enclosed in some region that includes both particles. So if I keep the particles far enough apart, this is a hard measurement to perform. So for this reason, the quantum states, the particular superposition is protected from the environment if the particles are kept far enough apart. And you'll see similar arguments, I imagine, for Majorana fermions. And this is really at the heart of these. It's this storing of the information non-locally for this that is at the heart of the protection from decoherence. It makes this good for quantum computing. Okay. So now, 3 particles. So if I have 3 particles, what can I say? Well, let's start combining their charges. Let's say the total enclosed charge here is 0. Then maybe someone can tell me what's going to be the total charge of all 3 particles. It's going to be 1, because charge 0 is equivalent. That's the same charge as the vacuum. So by the fusion rules, the total charge has to be 1. There's only one possibility. But if I have maybe the same 3 particles, but I draw them up here, and let's say the total charge is 1. In this case, what's the total charge of all 3 particles going to be? 0 or 1. So it could be 0 or 1. So really, these are 3 basis states for a Hilbert space. We have a 3-dimensional Hilbert space now for our 3 particles. Okay, that's good. But even at this stage, we see there's a subtlety arises. And to see that subtlety, let's focus on these 2 states here with total charge 1. There are 2 states with total charge 1. One state where the 2 leftmost particles have charge 0, one where they have charge 1. So here are those 2 states. This A can be either 0 or 1. So we have 2 states here. And the issue here is no one told me that I had to combine these 2 charges first. I could just as well have combined the 2 rightmost charges. And in that case, again, the fusion rule tells me this charge here can be either 0 or 1. And the point is, this is a human choice. You know, what basis you use is a human choice. Nature doesn't know. Nature doesn't care. And that's reflected in the fact that there has to be some unitary operation that changes basis from this basis to this basis. So my role as universe creator has become a little bit more complicated. I have to figure out how to change basis. So I have to introduce a matrix. This is the so-called F matrix. And in this case, the non-trivial content of this matrix is just this 2 by 2 matrix here. And at this stage, I could choose F to be any unitary matrix. In this universe of 3 particles, everything would be fine. However, there is a very strong constraint on this matrix. And to see that, let's go from 3 particles to 4 particles. Sorry. Before I do that, let me just also, so again, here, when I apply the F matrix here, I'm essentially expanding this state in this basis. But I don't want to keep writing the summation, so I'll use this notation here, this arrow labeled with an F. And here, I'm moving the solid oval from here to here. You can think of this, again, as a basis change from this basis to this basis, or a calculation where I expand this state or states in this basis in terms of states in this basis. OK, so 4 particles. And first, let me just show you that we can, using our 2 by 2 F matrix, we can still deal with 4 particles. So for example, let's imagine these 2 particles have charge 1. And let's say all 4 particles have charge 1. And then I have the 3 leftmost particles here could have either charge 0 or 1, because I'm combining a charge 1 object with a charge 1 here. And the point is, if I want to do a basis change, I can always think of these 2 particles as a single particle with charge 1. It's equivalent to really having 3 particles, where this particle here represents this pair, which has charge 1. And here I can apply the F matrix to do this basis change. And then back up here, it amounts to moving this oval from here to here. So I can, and so you can easily convince yourself you can perform arbitrary basis changes for arbitrary numbers of particles using the F matrix. And let me also emphasize, if this charge were 0, it would be trivial. If this charge were 0, these 2 particles would be equivalent to not having them, because it's the same charge as the vacuum. And we just have 2 particles with charge 1. So in that case, the F matrix is just the identity. And in fact, the only non-trivial case is when, for the F matrix, is when they're for Fibonacci anyons, is when you have 3 objects with charge 1, where the object could be a single Fibonacci anyon or a bunch of them, which has charge 1. And we carry out this, and the total charge of all 3 is 1. And we carry out this basis change. All other cases are for Fibonacci anyons are trivial. I'm mentioning this partly, and I'll go over it again, is because I did something, I assigned homework, and you'll need that. OK, I think I have, yeah.
Yeah, sorry. How did you group these 2 particles to one? I mean, you have number of particles as kind of another charge, and you can just you can just restrict yourself not to group 2 particles and just look at them as a one spin.
You mean, do I have to specify the total?
Yeah, I mean, you just look at those 2 particles as one particle.
Yes.
And then did this calculation for F matrix.
Yes.
I mean, is it always possible to do that? I mean, because you.
Yeah, well, either for Fibonacci anyons, it's simple. If they fuse to 0, it's like they're not there, and it's trivial. If they fuse to 1, you can treat them as a single Fibonacci anyon. And that's why everything for Fibonacci anyons, everything reduces to this case, and you only need this 2 by 2 matrix.
Number of particles doesn't matter?
Yeah.
Number of particles doesn't matter. I think, yes. Number of particles doesn't matter for what?
No, not even conserved or whatever.
Oh, no, the number of particles, oh, I see. No, OK, I was doing this, so we actually, well, actually that's, so the number of particles is in fact, in Fibonacci anyon theories, 2 Fibonacci anyons can fuse to make a single Fibonacci anyon. So in fact, the number of Fibonacci anyons is not conserved.
Oh, it's not possible.
Yes. It's not even conserved mod 2, which would be the case for, say, excitations in the toric code or something like that. So it's much worse or better. So maybe I'm running out of time, but I want to end on, let me put all of this together and show you what the subtlety is, at least, that we can address. I'll start addressing in the next lecture. So here we have 4 particles, and this represents a particular basis choice. I can label these ovals with all the possible allowed enclosed charges that are consistent with fusion rules. And what I want to do is now carry out a basis change, say from this basis to this basis. That's the example I just did. I just move this oval from here to here. And then do another basis change, moving this oval from here to here. And I think you can see in these, again, this is, if I think of this as a single object, it's, again, a straightforward application of this F matrix. And so this is a calculation I would do, let's say, if I wanted to expand a basis state in this basis in terms of this basis. I just apply the F matrix twice. However, as you may know, or maybe you can see, the subtlety is there's another way to perform the exact same calculation. So can anyone, is there another F move I could do here that might take me eventually to here? Does anyone? What I can do is I can focus on just these 3 rightmost particles and do an F move inside here, from here to here, or an F, apply the F matrix, change of basis. Then I can go from here to here, move the oval from here to here, and then finally, final step, move this from here to here. So again, if I wanted to expand these states in this basis, I could calculate the expansion either going this way along the top, or I could calculate it another way, along the bottom. And whenever there are 2 distinct ways to do the same thing, my role as universe creator, for my universe to make sense, I better make sure my F matrix gives the same answer. And that requirement is this is really an equation. This is the famous pentagon equation. And part of the homework is I'm actually asking you to solve it, because for Fibonacci enhance, it isn't that hard. And I'll have more to say about that, I think, when the next lecture starts. But I think this is a good place to stop. This is this self-consistency condition, and I want to emphasize in this process of creating this universe, really the only choice I had was this initial fusion rule. Once I fixed that fusion rule, everything else so far has been fixed. And we'll see this, furthermore, this completely fixes the form of the F matrix. And we'll go on to see even the braiding properties are fixed. OK, I think that's a good place to stop for this lecture here. So maybe if there are any more questions.
Yeah, so the 0x0 fusion rule, does it tell you that you cannot create one particle out of nothing? You have to at least create.
Yes. Yes, there's a super selection rule. The total charge is conserved. In this case, the total charge is either 0 or 1. But if the total charge of your whole system is 0, including, say, your boundary, or if you put it on a sphere for simplicity, so there's no boundary, then the total charge of all of your anyons is well, in that case, it has to be 0. Yes, you can't create a particle out of nothing. But the total number of particles, at least for abstract Fibonacci anyons, is in fact is not a good quantum number. Okay.
So it seems to me you have this rule for constructing the Hilbert space of this Fibonacci anyon. Is the claim that in the 12th fractional Hall state that these are the degenerate ground states you get with quasi-particles?
That is the claim. It's certainly true if the 12th state is a Reed-Rosai state. That wave function, I'm not sure I know the status of the mathematical rigor of this statement, whether it's comparable to the statement for the 5/2 state. But from a physicist's point of view, there's no question that if you have these fractionally charged excitations with charge E/5, they're not precisely Fibonacci anyons, but their differences are trivial at least in this context. And yes, this would be the Hilbert space for a collection of these particles. So if you want to think physically of these, you can think of these particles as these fractionally charged excitations.
Follow-up, is there a connection between the degeneracy of these excitations, these quasi-particle excitations, and the ground state degeneracy of the 12th state on a torus?
Yes, but to make that work, I have to, so as I say, I'm throwing away many details here. The actual non-abelian excitations of the 12th fifth state are given by this parafermion theory. And living inside this theory, there's a small subset of that is the Fibonacci theory. So I'd have to describe in more detail the quasi-particle properties of to get the ground state degeneracy of to count the number of distinct quasi-particles, which I don't know offhand. For the 5/2 state, it's 6 for fermionic. I should know the 12/5 state degeneracy. I can work it out during the break. But it's not as simple. If I had a model with just Fibonacci anyons, which people are sort of, there are recent speculations for ways you could actually manufacture Fibonacci anyons. You know, this paper by Mong and Alexia et al. And somehow, if I understand it, in those states you actually would get the twofold degeneracy you would expect if really your only quasi-particles were the vacuum in Fibonacci anyon. But for the 12/5 state, they're more you have charge E/5, 2E/5, 3E/5. So you have distinct electrical charges, and for each of those electrical charges, there are distinct topological charges. Just living inside that, there is this Fibonacci theory.
So these two ways of doing things, will they result in a different phase?
Not if you do it right. They better not. They better not. Lurking underneath all of this, there is sort of an arbitrary phase choice. Since these are basis states, I have to make a phase choice, and there's some gauge degree of freedom. I can always multiply my basis states by an arbitrary phase. But once I fix that, then it's not. These don't have to agree up to a phase. They have to agree.
That you can only combine the nearest.
Say again?
Is there a rule that you can only combine the nearest?
No. Although for me, the best way to think about that is I'd like to also include the tools for moving the particles around each other, and then I can really calculate the effect of, say, combining the charge here with here. But there's no reason, there's no rule.
Okay.
I could draw an oval.
So that would be another basis.
That would be another basis. And you can express that, you can again express that basis. To calculate that, I think we need a little bit more. Yes. Yes?
Is the truncation in the fusion rule very important for topological properties?
I would say yes, because if you don't have the truncation, it's ordinary. It's like ordinary spin.
But it's also non-abelian, right?
It's not. So it's absolutely crucial. It's not abelian. There has to be more than one term on the right-hand side.
Why the truncation makes different?
Well, I don't know. At least one sort of answer is if you don't truncate, there's a quantity called the quantum dimension, which tells you how the Hilbert space grows as you add particles. And for ordinary spin, the quantum dimension is an integer. It just reflects the fact, in this case, it would be 3 because these are spin 1 particles. And when that's the case, then you can have a local degree of freedom, like the SZ quantum number. If I have the 2 here, there's no reason why I can't have, for each quasi-particle, an internal degree of freedom, 1, 0, and -1. And in fact, you do for ordinary spin. And so for people, including people probably within some radius of this room who are trying to build quantum computers out of spin, that's a big problem, those local degrees of freedom. But the non-abelian anyons have many features like spin, but they don't have this local SZ. And in fact, for technical reasons, so the quantum dimension of these Fibonacci anyons, we'll find out, is irrational. It's in fact the golden mean. And for technical reasons, it seems that is necessary to have to be able to do arbitrary quantum computation purely by braiding. But I think the big answer is the truncation is at least connected to the fact that there's no local degree of freedom here. It's like you have spin, but only total spin quantum numbers. And so you don't have to worry about decoherence of the local spin.
So this truncation gives rise to non-locality.
Yeah, although in some sense, ordinary spin has non-locality. I mean, if I have 2 spins that are well separated, the total spin quantum number is some non-local quantum number. But in addition to that non-locality, one also has local SZ. And here, I think this keeps the non-locality and throws away the locality. But that's very sort of hand-wavy, intuitive sense for why it might be good.
First,
are these particles labeled? Second, how would I possibly compute the number of microscopic states and such as?
We will, I will do both of those in the next hour. So maybe I can, since we're running out, I think the break is, we're running into the break now, or do I have the time? So maybe I can, I will answer those questions in the next lecture.
Okay, let's thank our speaker again.